In this video, I'm going to look a little bit at the statistical properties of pseudorandom numbers. So as before, we can generate in MATLAB a set of random numbers. I'll call that my X samples, my samples distributed from 0 to 1, and I'm going to generate in this case 1,000 of them, and here they are. Now one thing I can do with that set of samples is I can histogram them. So the histogram function in MATLAB is called hist. So if I simply ask for hist of the X samples, hitting tab to get that to pop up, I get a histogram. Now if you look at the help for the MATLAB hist function, you'll see that by default I get 10 bins. So I can ask for that explicitly by hitting the up arrow key. I'm going to ask for 10 bins explicitly, and you can see that on the right here I've got 1,000 samples, and the mean value, the mean number of samples which have been placed into each one of these 10 bins is of course 100, because I have 1,000 samples in total. Now let's do that in a script. So I'm going to create a new script, and I'm going to call that histogram of uniform samples, something like that. And I'm going to create my X samples is equal to a set of 1,000 random numbers, and I'm going to histogram them. I'm going to do hist of X samples in 10 bins. So now if I do a close all and clear all at the top as usual, I'm going to call this hist test or something like that. I can run that, and you can see that each time I run this script, obviously I'm generating a different set of random numbers, so I have a fluctuation in the number of samples in each bin. So this is approximately uniform. You can see that the likelihood of having a value, a random number in any one of these 10 bins is equal. The probability is equal to 0.1. And if I increase the number of samples to 10,000, I should expect that the fluctuation goes down. And there it is. The relative fluctuation, the percentage fluctuation, is going down. But what actually is that fluctuation? Well, it will turn out that it's equal to, but not exactly equal to, the square root of the expectation value, the expected number of samples in each of the bins. So, for example, with 10,000 samples, as I have here on the left, then the rough value, the approximate standard deviation for the in the variation of the number of samples in that bin is 10,000 divided by 10, so that's 1,000, and it's a square root of 1,000, which is of course about 30. So the standard deviation of the height of each of these binned sets of numbers is about 30. And you can see that by eye, if I go back to 1,000 samples, then of course the fluctuation is plus or minus 10. Okay, so you can see that that's about right. We're going from about 2/3 of these bins lie between about 90 and 110, and a few lie further away. And of course, if I have enough of these, if I do enough of these runs, eventually I will see some of these bins having a smaller number. They'll lie some way outside 2 sigma, where sigma is 10. So about 1 in 20 of these runs will lie outside of 2 sigma, which might appear at first to be a fair distance away, but of course is entirely consistent with this statistical fluctuation. Now, let's see if we can count up. Let's do this this procedure of generating 1,000 samples and binning them, and let's actually have a look at what the standard deviation really is. So if I go to here, help hist, just to see what I can do with the hist function, as well as histogramming the values, I can also obtain the actual values that the hist function has returned. So if I, instead of asking for the histogram to be plotted, I instead ask for the number of samples in each bin, so I call that n in each bin, and x, as it says here, is the x centers. Okay, that's where the center of each bin is. We can run that, and now I'm just going to expand the MATLAB window a little bit. You can see that n in each bin, those is displayed here on the right, and the bin centers are pretty much at 0.05, 0.15, 0.25, and so, okay, because they go, that's the first bin is from 0 to 0.1, the second bin from 0.1 to 0.2, and so on. So what I can do is I can look at the fluctuation. I can look at the standard deviation of those values. So let's have a look at that. How do we do standard deviation in MATLAB? We'll do help. Is it STD? Possibly. Yes, STD is a standard deviation. So if I do standard deviation of n in each bin, the value is not quite 10. We might have to run this several times to get a better idea. So, well, let's do something slightly different. What we'll do is we'll say for I equals 1 to 100, and I'm going to run this calculation. I'm going to calculate, I should create a new set of samples each time, shouldn't I? So I'm going to calculate 1,000 samples. I'm going to histogram them. I'm going to bin them actually into 10 bins, and I'm going to, for each one of those samples, let's just look at the first bin for simplicity. So I'm going to call this first bin, and I'm going to accumulate 100 samples of what happens when I only bin the first. 100 samples of the number that lie in the first bin. Of course, that has a probability of 0.1 each time. So there'll be n in each bin, and that's 1. So I'm just counting up how many are in the first bin. So if I do that and just disp fbin at the end, just to look at them, let's run that. You can see that I have, on average, about 100 of those values. So let's just check that's true. So if I take the mean of fbin, and I'm going to leave off the semicolon for simplicity, just so we can display it quickly, and calculate the standard deviation of the first bin values, and save it and run it. Well, it looks like it's about right. Doesn't look like we're calculating enough of them yet. So you can see there's some indication that the standard deviation is actually less than 10. So it's approximately equal to the square root of the number of the expectation value of the number in each bin, but it's not quite that. So let's do that procedure 1,000 times. Let's take a look at it. So you can see that the mean value is about 100, and the standard deviation is less than 10. So why is this? Well, this shows that there is a rule of thumb in doing Monte Carlo calculations, which is when I have a set of samples and I divide them into bins or tallies or whatever you might want to call them, then approximately the standard deviation, if I just histogram those samples again, if I just to show X samples, so I just displayed them. So the standard deviation of the number of samples in this first bin, say, or any of the others for that matter, is approximately equal to the square root of the average value, which in this case is 100, the expectation value. So that's simply equal to the probability of being in this bin times the total number of samples. But the variance of the samples lying in this bin is actually distributed binomially. So this is the difference. So if we think of the number of a sample either being within this first bin or being in any one of the other bins, the probability it has of being in this bin is 0.1. So if you look at your statistical behavior of the binomial distribution, you will see that the variance of the number of samples in this bin is actually equal to the probability times n times 1 minus n, where n is the total number of samples. So if you calculate that, you will see that the standard deviation is a bit less than what you would guess if you just used the square root. So that square root approximation is approximately true, and that approximation gets better the larger the number of bins you have. So once you have 20 or 30 bins, it's pretty good. But for a small number of bins, and it starts to show itself at around about 10 bins or fewer, and of course it's particularly acute if you only have like 2 or 3 bins, as we will see in a later calculation, then the standard deviation is smaller than you would otherwise expect. Now you can see that on the left here, what we've done here is, rather than relying on a calculation of a mathematical calculation of the fluctuation in the number of samples that have lied in each bin, another way to obtain that statistical fluctuation is simply to calculate it directly. So you can see we've done this calculation 1,000 times, and we've directly calculated the standard deviation. So we can see numerically and check to see how important that numerical difference is between our approximate measure, which is that these samples fluctuated by square root of the expectation value, but is actually a little bit less because, of course, it's binomially distributed.